Hey kids! Kids! Hey students, hey mathematicians, it's Miss Hyder here. I know you're probably sick of seeing Mr. Riggs because, you know, who likes it anyways? Today we're going to be doing objective 143. Students will be able to understand slope and find slope from a graph. Pause the video and get that written down just so we can stick to our New Year's resolution of keeping videos short. The first vocabulary word that we're going to learn is slope. Slope is denoted with variable m, and my favorite definition, although you can find many, is slope is a rate of change. And the reason why I personally like this definition a bit is we are really familiar with rates. And rates, they are fractions or ratios or comparisons of two different units. So when we are comparing, right, unit 1 to unit 2, we can see the change of these variables. The reason why I really like rate of change is because we can see it as a ratio, where we're comparing two different units. Now, if you think about the x and y axes, the x represents one unit and the y generally represents another unit. So when we compare the y and the x, we can always also see that, and you've probably heard this, as rise over run. This is going to connect to two more definitions later on in this objective. Next, we have change. So the first thing I want you to think about is there are three different types of change, and then one that's a little bit off. But if something is changing, that means it can be moving in two different directions. That is positive or negative. So whenever you think rate of change or slope, you do have to think, is there a positive or negative inclination? There can also be something that has no change, right? You look just as bad as you did today as you do tomorrow. Nothing has changed, okay? So we have positive, negative, and 0. Mr. Riggs is going to take over from here.
All right, man, that's one tough act to follow. So we have rates of change here. One more way we can define rate of change, as Ms. Hyder has done so well, is this idea of the change in the y values compared to the change in the x values. Whenever you see this in math, by the way, I think it's really cool to know this triangle just stands for the word change. You'll see that mathematicians are oftentimes lazy, so if we can do things quicker with less effort, we try to do that. So when I see rates of change here, I'm also talking about the change in the x values compared to the change in the y values. Same idea as rise over run. So right now, I'm talking about a positive rate of change. Oh my god.
Sorry, I'm so sorry.
You scared me. So right here, when you see the word positive, if we're talking about a positive rate of change, we're talking about a positive slope. I put it in parentheses just because the focus is on a positive rate of change. The slope is the same idea. The definition, think about it as as your x values increase, so if you're at 1, then 2, 3, 4, as those x values increase, your y values also increase. And that makes sense. If our x's are increasing and our y's are also increasing, when we have a positive change, we have a positive rise over run. And slope, positive slope, goes up from left to right. So I draw just a random line. This represents positive slope. As my x's increase, my y's also increase. You can think about it, if you start at the leftmost point, you're going up. You're climbing up the mountain. From left to right, it's increasing. Now, we're talking about negative rate of change. We're still talking about slope. So we're trying to identify how can we tell if something has a negative slope or a negative rate of change. Very similar, but this time as, and you probably already guessed it. If you're ahead of me, awesome. Way to go. Again, as your x values increase, but this time your y values decrease. The downward arrow is just my lazy way of saying decrease. So this time, as my x values are increasing, getting bigger and bigger, my y values are going to decrease. And we can show that with a downward slope. So again, if you were to start from left to right, to show negative slope, it just goes down from left to right. You can see as my x values get bigger, so from left to right, my x values increase, my y values decrease in value. They get more negative. That's showing that positive and negative rate of change. I really hope that was in the image. Oh, you can see it. Awesome. All right, so zero slope, the biggest and first most key point I want to hit is zero slope is just what it is. It's zero slope. I want you to write this phrase, no slope, and I want you to cross it out. A lot of students confuse zero slope with no slope. They're not the same thing. Zero slope is a very specific slope, just like positive and negative. If we're trying to define again what exactly is zero slope, so I'm going to get even lazier. As x increases, I'm saying as the x values increase, just like we saw with these definitions, your y values do not change. You could also phrase it as your y values stay exactly the same. So as your x's increase, your y values don't change at all. So I'm trying to graph this idea. Again, I just have my x and y axis right here. Let's say I had an x value of negative 6. And then when x is negative 5, we'll say this is point negative 6, we'll say 3. And then as my x values start to increase, my y value stays exactly the same. So that might be negative 2, and then my y value is the same. Maybe this is positive 3, so x is 3. But again, my y value stays exactly the same. That's what no slope looks like. Looks like a horizontal line, okay? And you can think of it as this, like, let's say you went to a roller coaster ride, you were at an amusement park. I use this to conquer my fear of heights, way to go me. But if you're on this ride right here, how much fun would you be having? And the answer is zero fun. Because that ride would be the worst. You're actually just sitting there. Like, there's no hill. Like, it's not even, it's like, this is the ride. Imagine how boring that would be if you were just sitting on that ride. That might help you remember what zero slope looks like. Think of how much fun you're having here, and that's zero fun. Now, undefined slope, this is actually where the term no slope makes more sense, but the better way to phrase it is still undefined. Like, there is a slope, we say it's undefined. No slope is more acceptable there. This is saying, well, this is actually the most different. Give me a second. So this is the strangest definition. It's saying as your y values, so notice how this is the only definition that starts with y values. As your y values, I'm just going to say change. So as they increase or as they decrease, your x values, let's say your x value stays the same. So your y value is one changing with undefined slope, but your x value stayed exactly the same. So let's imagine this. If I had an x value of, we'll say this is negative 3, or say this point is at negative 3, 2. With undefined slope, your x value is never going to change. So you're always at negative 3, and then maybe 4, negative 3, negative 6. This is what undefined slope looks like. It's a vertical line going straight up and down. That's undefined slope. And now, I do have another fun way to think about this. Well, maybe not so fun, but you got really bored of that zero fun amusement park ride, so you decided to look over at this one and try it out, but this looks a lot more dangerous because in this one, you're not having zero fun, but you might hurt yourself, you actually might die. So when you think of undefined slope, think of right there, undie. The word die kind of comes out of undefined. This is the kind of slope, this is the ride you don't want to be on. Like, bad things are going to happen to good people there. So, I'm just going to leave it there. Alright, we're on the next page, but I'm not going to explain anything here. I want you to figure it out, knowing that it is hard. I want you to answer these questions, but I think you'll be pretty good at. I think these will be great answers. There's actually one word, the same word that goes into both blanks, and I want you to figure it out. It's actually going to be the start at our class tomorrow for the year 2017. But my biggest piece of advice is pencils. please use pencils on this part because we are likely to erase what you have here. If you use a pen, it's just going to make your work really messy. So please use a pencil, finish that page, we're moving on. So we're here on page 16. Again, I'm not going to explain much to you outside of this. You're trying, given all of these lines, you're trying to answer these 6 questions. It's asking about which one has the smallest positive slope and the smallest negative. I fully believe you all can figure it out, or at least do enough to get our conversation started tomorrow. As you're answering each of these questions, think about this definition of slope we haven't mentioned yet. Slope can also refer to the steepness of a line. So when you're trying to answer question 1, try to answer which of the following of all of these lines with all different slopes, which of these slopes has the smallest yet positive slope? Question 2, which of these has the smallest yet negative slope? Make sure you have very clear answers from 1 through 6, and then Ms. Hyder's going to come up and not rap, but she's going to say some really cool stuff about this picture right here.
Alright, we are going to talk about slope and what rise over run really means, and then together we're going to come up with the formula. So we know slope, denoted M, is rise over run. And Mr. Riggs also mentioned that it is the change of y over the change of x. So whenever we're finding change, we are finding the difference, right? So if I'm looking at any 2 points, I'm going to call, and it's really, really up to you, as long as you pick a point and stick to it, I'm going to call 4, 3, point 1. And I'm going to call my second point 8, 5, point 2. Now, I am calculating the change from my first point to my second point. If I'm doing that, I can't just draw a line through your guys and be like, oh, that's a change, right? We know that there are 2 axes or 2 directions, and to get from this point to this point, I have to either go up, down, left, or right. So since we're usually dealing with x first, or at least I personally do, I'm going to just see how many units to the right I have to move in order to get to this point. So I went 4 units to the right, or plus 4. From there, I still have to go up, so I went 2 units up, which is plus 2. So just visualizing this, I can see that the change of my x was 4, and that's in the denominator, and my change of my y was positive 2, and that's in my numerator. Now, this was a really, I strategically chose these 2 points so you can visually see it, but if I didn't want to draw it out with graph paper, because we don't usually carry around graph paper, maybe, I don't know, but not generally, right? But what we can do is we can actually find the change of our y's and the change of x's by identifying what are our y's and what are our x's. So if I could just quickly rewrite, my first point, point 1, is 4, 3. My second point that I chose was 8, 5. If I want to find the change of my y's, here are my y values, okay? It really doesn't matter which one you do first, and we'll talk about that a little bit more, but I already chose this to be point 1, this to be point 2. I like to keep things positive, so I'm going to start subtracting from this point, but I'm established now. I'm going to start with this one. So I'm saying, okay, 5, which is my y coordinate, minus 3, which is my y coordinate. And then I would do the same, since I started with this point first, I would do 8 minus 4. And you'll see that you still get 2 over 4. So we're just going to summarize on this side right over here. If we know that slope is rise over run, and that's the same thing as change in y over change in x, given any 2 points and I'm going to call them x1, y1, that's my first point, and x2, y2, that's my second point of my choice. We can find the change in y over the change in x by simply subtracting the y's. y2 minus y1, giving you your, again, change in y, over the change in x, which is x2 minus x1. And that is where that formula comes from.
If you don't want to make a really tangible connection, connect this really clear work to the problem Ms. Potter just went through over here. It'd be fun to actually substitute in. You would once again get to that 2/4 rate of change.
Mr. Riggs, do you want me to do one example really quick?
No.
Nah.
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 Nah.